But Oh, thank you all for coming this evening, or afternoon, evening, depending on how you consider evening. This is a special meeting of the East Tennessee section of the American Chemical Society. I'm Stephen Neal, the chair this year. And I want to again welcome everybody. See a lot of the officers here this evening, and that's wonderful to see everybody here. I'd like to, at this point, kind of turn it over to Al to do some of the background on the Lynn lecture itself. And so with that, get it done.
Thank you. Thank you.
Go through it.
All right, welcome again. I'm Dr. Hazari, recently retired from the department. Laboratory director and lecturer. And I am the counselor for the local section along with Dr. Laris. Oh, here he is. So we have two counselors in the East Tennessee section. Well, the Lynn lecture series has a long tradition. I hope you got a little glimpse of what I'm talking about by looking at the little brochure here. But it started like over 60 years ago. And a lot of prominent scientists and chemists. Many prominent scientists and chemists have come and stood right here and talked to us about their work and research. And today we are still in good company because Dr. Daniel Nocera from Harvard University is with us. And at this time, I'd like to ask him to come forward here for a second or two. We really appreciate you swinging by and accepting our invitation to speak. And we'd like to present you with this plaque. It says, Dr. Daniel Nocera, 2016, SC Lind Lecturer, East Tennessee Section of the American Chemical Society. Thank you. Right here. In addition, we'd like to give you a little token of our appreciation. It's a check. Okay.
Drinks on me.
Yes. And again, thank you for coming over all the way from Harvard University. And I'm sure you'll hear more about Dr. Nocera's background from Dr. Barnes. I'll ask him to come and tell us more. Thank you.
I guess I'll use the microphone like everyone else. I'll do it. Thank you. So, there we go. Let me introduce our seminar, kind of the professional background of our seminar speaker today, Dr. Daniel Nocera. He's currently a member of the faculty in the chemistry department at Harvard University. He has the title of the Patterson Rockwood Professor of Energy. It's the only professorship at Harvard that is the Professor of Energy, but it is not unique to Harvard. Actually, your previous title at MIT, was also Professor of Energy, so it's a kind of a theme of your research. We'll kind of hear about Dr. Nocera's research into how to utilize solar energy to produce renewable chemicals and fuels, and it has been kind of a continuing interest of yours for many, many years, I believe. But let's go back to his early career. It's always interesting to kind of trace where someone has come from. He began his education at Rutgers, got a BS in chemistry, continued with a PhD at Caltech, then began his independent career as a member of the faculty in Michigan State, then moved to MIT where, as I said, he was the Dreyfus Professor of Energy there. Dr. Nocera's efforts in scientific research and in championing renewable energy development worldwide have earned him a widespread recognition and awards. Too many to go through by any means. He's a member of the American National Academy of Arts and Sciences as well as the U.S. National Academy of Science, which is one of the more important policy-making boards in the U.S. I believe you've also founded at least one, possibly many or several companies. One is Sun Catalytics, which I believe has just been kind of bought on by Lockheed Corporation, whatnot. Dr. We're basically, these companies in a large measure have been kind of to take your fundamental research and bring it to an application stage in some cases. Has that kind of been the theme? Yeah, okay. With that, let me turn the floor over. We're going to hear a different seminar than was planned, but I think you'll find it very interesting. Thank you very much for coming.
Thank you. So let me get this. Right, so what I did is I'm disorganized, and I thought I was speaking at ORNL today. So I was giving the general talk, and then at ORNL, and then at Tennessee, the abstract I sent you, I was going to give a more specific talk on the catalyst development, which I'll mention here. So I'll use 3 slides to mention the catalyst, but I actually have a whole talk around that catalyst design, because that's the key. But there's some Oak Ridge people here, and I have a feeling they're going to say, no, just give the general talk to us too, but we're going to find out. I'm going to let them decide. So it's a pleasure to be here. I've loved being in the department. It's really nice to see all the new young faculty. I've met them. You know, it's always nice to go to a department and see so many junior faculty. It means it's a healthy department, and it makes it an interesting department because you got all these new ideas, and everybody's energetic, because as you get old like me, you just start to move slowly. And being professor of energy is horrible, because when they see me falling asleep at my desk, it doesn't look like a professor of energy. And then they say they're going to take my professorship back. The other reason it's nice to be here is I couldn't get here because, is it ESPN, John? Is that what you said? Yeah. And then I didn't realize it's my family friend's football team who was here. Can you believe it? As a matter of fact, don't worry. I don't care if they win or lose. If he hear this, is this not getting videotaped, right? He'll kill me. But during my talk, he said he's going to text me because the team is getting to the Marriott out at the airport at 5 o'clock, and he wants me to come over. He thinks I'm going to hang out with him all weekend to go to the football team. I don't know. But you might see me on the sidelines if I delay my trip, because I usually stay on the sidelines with these guys. But I think you have a good chance of winning. I think Nick is a little worried about this, a lot worried about this game. So. All right, so what I want to do, forget football, I want to talk about this today, and I'll set the problem. Since I knew there were I found out there would be a lot of graduate students here, this is why it's a good general talk, or I wanted to give it, is I wanted to show you how we chose the problem. There's a problem selection. So when you do science, you have to figure out, why am I working on a problem? And I literally will show you the logic path that we use to choose this problem. And then I'll talk about science. So this is an identity relation, not an equation. That is exactly equal to that. It is the same thing. So in math, it's called identity relation. And what it is energy. And so you can say energy, or I could say population, gross domestic product per capita, how rich a country is, how much money in the country per person. And then this is energy intensity. That's what this is called. And that means I grow a GDP in 2016. I don't care what country, you have a GDP. And then next year, you used less energy, but you got to the same GDP. That means you conserved. And so conservation, which is a word that it sounds not very, it's kind of subjective. It's not a subjective number, it's a math equation, and it's how much energy you use to grow your GDP, and depending on if you use more, you're not conserving to get to the same GDP. If you're using less, you are conserving. And so when you multiply this equation out, you're going to find out that energy is energy. So once I know these 3 numbers, I can calculate energy use. So that's number 1. So we did that, or I did that a few years ago. And I could calculate what we use today, because I can look all this data up. That's not hard. It's all on websites. You can go to a number of websites and get all this data. And then I can also project to the future. So the way I'll project to the future is I'll say, what will the population be in 2050? It will be, in this calculation, I used 9.4 billion people by 2050. I can figure out what the GDP per capita will be globally. It turns out that the global per capita income per population has grown 2.3% per year worldwide for the last 100 years. So I can take 9.4 billion with the 2.3% predicted GDP growth on average, and then I have to make an estimate on energy intensity, which I did. I'll explain that in a minute, and that gets me to a number of 32 terawatts. Now, terawatt is power. That's not energy, right? It's joules per second. So I use that interchangeably sometimes because power is easier, because you don't have to worry about how much energy am I talking about, a year or a day or whatever. So it's burn rate, energy per unit time. So the way to think about it from an energy perspective is the world in 2012 has a 16 trillion watt light bulb on, and it's providing the energy to keep the 16 trillion watt light bulb lit forever. That's what you're doing. And then in the year 2050, you're going to be at 32 terawatt light bulb. And you all know that mostly that is coal, oil, and gas that is the power base to this, or energy base to this power. So how did I get to this number? It's this energy intensity number. I made an assumption that every bit of energy you use today, you'll save in the future. So in my calculation, to get that third term, I assume by 2050 the world would be conserving 16 terawatts, which you won't. So this is a lower number, but I'm an optimist. All right, so I'm hoping you will. And so if I make that assumption, and you're being very good citizens for the planet, you're saving 16 terawatts, why do you need so much extra energy? And it's because it's for the people you can't see, and it's the poor of the world. So in the next 40 years, the 16 terawatts is going to be driven by 6 billion new energy users. There's 3 billion low energy users. Actually, 1.6 billion people have no electricity as I'm speaking now. The other 1.4 are low energy, so there's 3. And then most of the new 3 billion people coming into the world are coming into that part of the world. And so that new population of energy users, and I call it non-legacy world. What does that mean? You live in a legacy world. You're living in a world where the energy infrastructure has been built. The wires are in the ground, the power plants are there, the nuclear plants are there. So you have whether you like it or not, it's very hard for you to adopt a new energy infrastructure because you spent a lot of money to build the one that you live in now. But in this part of the world that we're talking about, the energy infrastructure hasn't been developed. As a matter of fact, working with economists at the University of Chicago, they're now calculating the number, and it looks like, I've always been interested, why don't you get a new energy infrastructure? So everything I talk about today, I give lots of public talks, you know what they first say? ExxonMobil is going to stop you from doing this. No, they aren't. It's just pure economics. Right now, the estimate is just on your fossil fuel-based infrastructure, you've spent $8 trillion. And you've paid it off. So if you have a paid-off $8 trillion investment, you're going to be the last people to adopt a new energy infrastructure because it's free. $8 trillion is now free, paid off. Has nothing to do with oil companies. All right? And so that's why the legacy world is going to be the slowest adopters. And it turns out this part of the world, which you'll call the poor parts of the world, I don't like that, let's say non-legacy world with no infrastructure or a big infrastructure, they're going to be the quickest adopters. And so what we thought is we need to give or develop energy for that part of the world, not this part of the world. And then to do that, we decided it should be low capex, distributed, and available to all. Because now, once it's centralized, somebody owns it, and you have to get it from them. And you set up a market model to get a return on investment. I'm going to use just a little bit of business words and policy words. Low capex is low capital expenditure. Usually, you build energy at high capital expenditure. Somebody puts money out for it. Then they set up a business model to recover their money. So it's going to have to be a new model of energy available to all. And that says it should be simple. I'm going to explain that in my next slide. And if you're going to have low capex and simplicity, you better have simple engineering. I'm going to explain this. Simple engineering means lightweight and highly manufacturable. So what do I mean by that? So here's a curve. This curve right here, by the way, this is what the research I do. So my research is Google. So I go on Google and I make Google plots. And then I run into my group and I say, look what I just discovered. And then they say, you go back to your office and let us keep doing science here, Nocera. So since they won't listen to me, you have to. You're going to hear one of my Google discoveries. And what this is all I did is take the price of a Boeing 777 and I normalized it for its weight. And then I said, how many do they make a year? 74. And then I put that down. And then I did it for all these other machines. And I have a curve. That's a manufacturing curve. It's pretty remarkable. I have a manufacturing curve just based on the weight of something and its cost normalized versus the number produced without worrying too much about the technology. Now, what this doesn't work for is IT, information technology, Intel chips, right? Because they aren't made like you make machines. It doesn't work for commodity chemicals. It doesn't work for pills, pharma, because in pharma you'll pay anything to stay alive, right? So that becomes a non-market-based model. That becomes something else. Live forever, which is what most Americans think they can do if they fund medical research at huge amounts of money. So that isn't how these things. These are machines that you build. That's how you build your energy system, or anything you manufacture a lot, which you'll have to for an energy system. And it works for this. It really does work for that. So there's a CTO, Chief Technology Officer of McDonald's. I've met him, believe it or not. I didn't even think that McDonald's would have a CTO, but they do. And I asked him just to go back and tell me the weight of the hamburger, the cheese, the bun, tomato, lettuce. Comes out to $10 per pound. Okay? So that's interesting because we build energy systems over here. You build only one of them. They're very heavy. And when you take the minimum cost of manufacturing, $10 per pound, $10 per pound times heavy comes out to $1.5 billion. So that's high capex. You need to have $1.5 billion to build your power plant. All right? And then what you do is you set up a business model. I now have control of the energy. You want it, I'll sell it, and then you give me money. And then depending on how much of a return you want, return on investment, you set up the price of energy. So if you want to pay off your capex in some number of years, that sets your business model. That's how we give out energy, and it's centralized. So one big heavy thing that's centralized. It doesn't work for the 6 billion people I talked to you about because they don't have enough money, and if they don't have enough money, they can't pay for the capex, and there'll be no investor who wants to set up this business model I just talked about. And so if that part of the work, if that doesn't work, we turned our eyes to here. Now this is, I'm telling you, the logic path for choosing the science problem. And literally, this was important to us because we started thinking, could we make the McDonald's hamburger of energy? So can you literally make an energy system the way McDonald's makes energy? So that's what we set out to do. And that, if you think of a hamburger, I'm going to talk about it in a different way. what would McDonald's business model look like if they did it this way? Did you ever think of that? They would make one big hamburger. You would all drive to it, take a bite out of it, and drive back home again, right? But they don't do that. What they do is they make a bunch of small things in a distributed way, and they hand them out. So we said, could we build an energy system like that? And that starts to give rise to lots of interesting science problems, right? So what is lightweight, highly manufacturable, and distributed? Leaves. And they use an energy source that's available to everybody. That's my other criterion. You have to make sure the energy is available to whoever is there. And so what does a leaf do? And I'm going to briefly talk about photosynthesis from a functional point of view. I don't want to get into all the biology. So what a leaf does is it takes sunlight in. You give the plant water. The first thing the leaf does is it splits water to hydrogen and oxygen. So it takes the OH bonds of water, rearranges them to hydrogen and oxygen. The hydrogen is stored as a solid form of hydrogen, NADPH. Okay. Then what it does, you all think biomass, wood, cellulose, leaves, crops. That is not a solar problem. All the solar energy is needed only for water splitting. The biomass is a dark problem. H2 plus CO2 makes biomass at night. And I'll come back to the thermodynamics for that later on. So the first thing is a leaf uses sunlight to split water to give high energy fuel, which is hydrogen. And then it stored the hydrogen with CO2 in the form of biomass, not for reasons of solar energy storage. It already stored solar energy. It makes the biomass because hydrogen's a gas and the plant didn't know how to store hydrogen. So it stores hydrogen. This is a hydrogen storage problem in terms of biomass. All right, so that's number one. So we want to do photosynthesis. That people have been trying and talking about a lot for a long time, since 1912. And so here's a famous photochemist. That's an Italian photochemist called Chimichon. He was at the University of Bologna in 1912. And what he said is, boy, it would really be nice to not be using coal, oil, and gas. And if we could use solar energy, that would be nice for society. And then he said to master the photochemical processes that have been the guarded secret of plants. And he said that in 1912 in Science. You can get that article. Now, the problem, why hadn't this moved very quickly? It's because, first off, people didn't do this. I'm going to show you in a minute. What they did is didn't do photosynthesis. And I'm going to now break this down even further, the solar energy piece. And that was that the leaf brings in sunlight, and then it does charge separation inside the photosynthetic membrane. So this is the crystal structure of the photosynthetic membrane discovered now in 2006, only 10 years ago. And so when the sunlight comes in, it moves an electron one direction and a hole in the other direction. That's a moving charge, current, but no wires. Then it stores the charge in cofactors. The manganese-oxygen evolving complex gets the hole, and an iron reductase in photosystem 1 gets the electron. And it does it one time, a second time, a third time, a fourth time. Once the cofactors have been charged up with 4 units of charge, they then become catalysts, and they convert the water into O2 and 4 protons and 4 electrons. The protons run around, that's over here at the oxygen evolving complex. The protons run around to the iron reductase where they get combined with the 4 electrons to make hydrogen. All right? So what does the leaf do? It takes sun and water, it puts it in an energized current. It then stores it like a battery. That's what batteries do. You store charge on metal centers. But the leaf then knew, I don't have enough energy density storing charge on metal centers, so it converts the stored battery charge into a chemical compound which has higher energy density of fuel. All right? So we said, could we do the same? So now you start thinking differently. Can I make a material do charge separation, unit at a time, times 4, store the charge in cofactor, I'm going to use a different word, catalyst, charge it up like a battery, 4 holes, 4 electrons, then do water splitting. And I could duplicate this part of the leaf. And then the question is, could I even do a dark reaction? Because hydrogen might be a problem in storing it even in our society. Could I make a fuel? So now you see the lineage. And it all has to be done cheaply. So all the science I invent has to be done very cheaply. That's not how we worked as a field. What we did is called liquid junction photoelectrochemical cells. That goes back to the 1970s. Now, why isn't that? That's everything you hear about. When you take a semiconductor, I'm going to shine light on it and do water splitting. Now, what are they doing there? They're mixing up photosynthesis separated charge from chemistry. A good semiconductor does 1 hole, 1 electron separations. That's all it's built to do. A good catalyst needs to do 4 electron, 4 proton chemistry. If I'm trying to make a material that's a good semiconductor, by definition, it's going to be a lousy catalyst. If I try making a good catalyst, it's going to be a lousy semiconductor because what a physicist would call the 4 holes and electrons are trap sites in my semiconductor where I get charge recombination. So what's a liquid junction photoelectrochemical cell? People for years were trying to make the magic semiconductor that absorbed the light, did charge separation, and did all the chemistry. And that still goes on today. And that's a liquid junction. We, a few years ago, said, no, we're going to be like a leaf. We're going to do what's called a buried junction. We'll take a photovoltaic semiconductor, bury it between 2 conductors, and then charge relay the whole 1 electron and 1 hole at a time into catalysts on the conductor. So now my chemistry is separated from my physics. It's that simple. And I can optimize both of these independently. There's other subtle things. And that is, when you have a conductor, you can think about it, there's an infinite density of states to put electrons in holes. So the Helmholtz layer is very thin in a buried junction. And then the second thing is sometimes you'll see people show what are called flat band potentials, where the hole and where the electron are relative to the chemistry. And that's because the semiconductor is trying to do the chemistry directly. But here, I don't need to match my flat band potential to my chemistry because it can move around because of this infinite density of states. So this buried junction doesn't look like this, but we started thinking that's really photosynthesis, even though people use the word artificial photosynthesis for liquid junctions. They just didn't understand the biology well enough. So we set out to make that. And the first hard piece is water splitting. I got to split water to O2 and 4 protons and 4 electrons. That's a 4 proton, 4 electron process. So Matt Cannon, many years ago in my group, 8 years ago, figured out you could oxidize cobalt 2 plus to 3 plus, and in the presence of phosphate, this would form. And that thing does water splitting. So my other talk is going to be all on this and why did we choose cobalt and the design principles for making this work. I'm just going to tell you what works. It works really well. It looks like the oxygen evolving complex in photosystem 2. The oxygen evolving complex in photosystem 2 is a cubane, so cubane, cubic. There's 4 manganeses. One of them's a dangler. It's called the dangler. The other corner is a calcium ion. That looks a lot like that. If I take manganese and replace it with cobalt and do a head-to-tail dimerization, so I'm going to do that now, replace manganese with cobalt, head-to-tail dimerization, do a 45-degree rotation, I get this piece of the cluster. So this is all fused cubanes. And in place of calcium, sitting above this tripod of oxygens is sodium or potassium. So structurally, it looks like OEC. It self-assembles. You take cobalt 2 to 3 in the presence of phosphate. You don't need some complicated synthetic inorganic chemistry here. Just throw them in solution, oxidized cobalt in the presence of phosphate, this forms on the electrode surface, and you start seeing bubbles come off, oxygen. The oxygen evolving complex assembles, that Q vein assembles from manganese 2 getting oxidized to manganese 3 in the membrane, and then it self-assembles. The electron-proton inventory, the 1 electron-proton piece, which you've got to build up 4 times, is exactly the same, mechanistically. Don't have time to talk about it. The part I want to stress is self-healing. This OEC heals itself. Every 30 minutes, the oxygen evolving complex, the membrane gets corroded, eaten up because it's making singlet O2. The plant pulls out the entire D1 protein in the photosynthetic membrane, reinserts a new one, re-self-assembles the OEC and keeps on going every 30 minutes. Every single plant you see, every chloroplast. It's unbelievable. So we said we have to make this self-healing. I need to be able to just have it run all the time. So what do I mean by self-healing? What we do usually is repair in chemistry. So a catalyst runs, it dies, it deactivates, then you chemically reactivate it and put it back into a catalytic cycle. Right? And the language we use is turnover number. Like, what's the turnover number? How long did the catalyst work before it died? In a self-healing catalyst, which I'm going to explain to you how to make in a sec, I put an equilibrium inside the catalytic cycle. That means turnover number is infinite. As long as the catalyst is working, I have an equilibrium inside the catalytic cycle. It will always fix itself. All right, so that's self-healing. So we set out to make, and there's not matter of fact, you're going to hear an energy talk, we still have not found a self-healing catalyst. This is the only group of catalysts we know that are self-healing. So how do you do this? And what I'm going to do is just tell you that the rate law, we can use electrochemistry and build a rate law for the oxygen evolution. And what we know is the pre-catalytic state is a cobalt-3, cobalt-4. Now, I'm writing cobalt-4 oxo as cobalt-3 oxyl because when you're on that side of the periodic table, so here's cobalt right there, right? There's iron over there. So at the iron manganese, you have empty d orbitals. Since they're empty, oxygen can donate into them and you get metal-oxygen multiple bonds. When you're on that side of the periodic table, all the d orbitals are filled, the low energy ones. And so therefore, you can't make multiple bonds. So what happens is the cobalt-4 is so oxidizing, it steals an electron from oxygen. And it makes a cobalt-3 oxyl. That's the pre-catalytic state. That's this state right there. Then in a 1 electron, 1 proton reaction, and that's the rate law for oxygen evolution. So it's inverse first order in protons. So when I change the pH, the reaction gets faster, or I can lower the potential, and it goes in 63 millivolts. Nernst's law is 59, so it's a Nernstian 1 electron. When I increase the overpotential, so this is the potential beyond the thermodynamic potential of water splitting. So if you remember freshman chemistry, H2O to O2 plus hydrogen is 1.23 volts, uphill. So when I go 0.27 beyond water splitting, this is the current I get. And this is a log scale. And then every 64 millivolts, again, every Nernst jump, I increase the reaction by an order of magnitude. Okay? So that's the 1 electron. But here's the rate law for oxygen evolution. I can also build a rate law, which I did here, for self-assembly. So I can watch. I told you the catalyst self-assembles on an electrode. So I can take a thing like a quartz microbalance, and I can watch how much catalyst builds up, and I can figure out as a function of cobalt, proton, phosphate, and number of electrons, and we get that rate law. And here's the mechanism. Andrew spent his whole graduate career putting that mechanism together. And you can read about it in JAX. what I want to do here is show you here, remember now this is self-assembly. Cobalt ions get oxidized to cobalt. So we oxidize cobalt 3 to cobalt 4 on the electrode. Cobalt 4 sees cobalt 2 in solution. There's an electron transfer. I get 2 cobalt 3s it lays down. Then I oxidize this to cobalt 4. It sees another cobalt 2 in solution, more lays down. That's how it grows. So here's that rate law. Here's the rate law for OER. I highlighted the green because you have an inverse third order for self-assembly, an inverse first order for oxygen evolution, catalysis. So let's do this experiment. At pH 7, here's the rate law, the real data, and then I put a line underneath as that rate law plotted as a function of potential. And you can see it perfectly matches. We then take the red line here, and then we measure how much cobalt we lay down. So there's that rate law. So now what happens? At pH 7, where I can make oxygen at 1.15 volts, I'm making oxygen at pH 7, I have an overpotential to drive self-assembly. So if any of the catalyst decomposes while it's doing oxygen evolution at 1.1 volt, that potential is plenty to drive Andrew's self-assembly process. So that's the equilibrium we put inside the catalytic cycle. This catalyst runs forever, as long as it's working. If I take the potential off and drop the potential way down below oxygen evolution, then you'll see it dissolve. As soon as you put a potential back on the electrode to do it, all self-assembles and starts working again. Right? So that's interesting. The other important piece of that is because it's self-assembling, it's always fixing itself. So if there are defect sites, it fixes it. So all catalysts that do water splitting need pure water because you get junk in there. In this catalyst, you can use Boston Harbor, you can use salt water, you can use a puddle on the ground, you can use the Charles River, you can use human wastewater. Why would you do that experiment? Because your most annoying student, Yogi, you make him do the urine experiment, and it makes you feel good as a research director. Get him back. But the other reason why Yogi did that experiment is what happens if you take wastewater and split it to oxygen and hydrogen? When you recombine it, what do you get? Clean drinking water. So we set out, this was a science problem. How do you build a self-healing catalyst for energy, which I'm going to talk about, but all of a sudden I now have a way to give distributed clean drinking water to people on the side. The other important piece, remember who my clientele is for my science, it's the poor. So say I build a great catalyst system, but oh, by the way, I have to distribute 18 mega ohm very pure water globally. That kills my hamburger. Hamburger might work. I'm going to show you how to build a hamburger. But then I have to give clean drinking water to the poor. There's no way this is going to work. Now, if they find any water source, including their own human waste, they're good to go. So this was very important to us, the science discovery, how to build the catalyst. And so that's why I have a whole talk on the design principles for that. It also means, since I can use any water source, more importantly, I can be with pH 7 water, it's not harsh conditions. If I have to be concentrated base or concentrated acid, I have to have heavy engineering. I can't have concentrated base or acid, see metal parts. There's a whole bunch of problems. Now, in a simple condition means I can integrate chemistry to physics in an easy way. I'm going to show you that in a minute. The other thing is I can interface to biology because biological organisms can live at pH 7. I'll show you that advantage. So one of the take-home lessons here is we set out to make a self-healing catalyst, and that's opening up all these other possibilities. So how about integrating? Because the problem I have with this catalyst is it doesn't absorb light. All this catalyst is built to do is the 4-electron, 4-proton reaction to make O2. So now how do I get light into it? The first thing is we put it on a transparent conducting oxide, fluorinated tin oxide, because I'm going to be making oxygen here. And oxygen, if I put it on, say, silicon, Si plus O2 makes sand, SiO2. So I have to protect my silicon with a coating. Then I have to make oxygen. I told you I could make oxygen at pH 7 at 1.15 volts. This silicon is a single junction silicon. So what you do is you take a piece of silicon, and then I have to put a negative charge and a positive charge in it. Now, why do you do that? You need to put an internal voltage ramp, because when I shine light at silicon, I make an electron and hole, they'll just recombine with each other. So you have to put an internal electric field in the silicon so the hole goes in one direction and the electron goes in the other. So what you do is on one side you dope it with something negative, right, phosphorus. On the other side you dope it with aluminum. And that puts an internal electric field. This isn't our invention. This is like run-of-the-mill applied physics. This is how you build junctions, right? So we read the Applied Physics Junction book, and we built an NPP plus silicon junction. Now, the problem is, outside of me not having an eye there, which is the first time I've ever noticed that, so that will be corrected, is that silicon generates only a 0.57 volt potential, okay? And that's what is in the band gap of silicon. Actually, theoretically, this should be 0.7, but we could get to 0.57. That's not enough voltage to split water. So I'm going to have to put leads on here to make this work. That energy I have to count to my device, and that's going to make it inefficient. But we didn't care. We just wanted to know, could we use this as an electrode? And you can. So if I put this in a glass of water with cobalt ions in solution, when I churn up my potential at 0.98 volts is where we oxidize cobalt 2 to 3. Then when that happens, we lay the catalyst down in that self-assembly process. Then when you go further, when I get by 1.2 volts, I get a lot of current because that's where I'm making oxygen. So right now, I'm using this heterojunction just as an electrode, just like you would do any electrode experiment, like we first did to invent the cobalt catalyst. But this is different because it's a single junction. So if I have, let's say I'm going to run this at a milliamp, I need 1.25 volts. And that's what this is right here. So I get to 1.25 volts, and now at a milliamp, and I see the oxygen production. But now this is a special electrode. If I turn or just take this electrode out into sunlight, the sun generates 0.57 volts internally. So that means that applied voltage I'm adding here, it's 1.1 in the dark, I should not have to drive it as hard because the sun's going to make an internal voltage. And you can see at any driving voltage I put on this electrode, when I put it in the sun, I almost capture or recover my full voltage of my junction. Because now I only have, at 1 milliamp, I don't have to put 1.12 in it. It's reduced by 0.52 volts because I'm generating an internal voltage from the silicon. So this isn't rocket science. If that's a single junction, I can do this, right? This is a little different. I took amorphous silicon. So now here's where, because I've separated chemistry from physics, I can do a good applied physics job of making a good light absorber. So I'll take amorphous silicon. Amorphous silicon has a strained lattice, so it absorbs at 400 nanometers, right there. Then germanium, bigger element below silicon. I dope germanium into the silicon. I relax the lattice, and depending on how much germanium I dope, I can move this to anywhere I want in the visible spectrum. So I'll dope enough germanium to make that. Then I'll even dope more germanium into that germanium, and I'll stop it there. And then I take that plus that plus that, and when I take that, that's the total absorption spectrum. That almost perfectly matches the solar spectrum. So now I'm collecting all the light. You can think about this as like 0.5 volts plus 0.5 volts plus 0.5 volts in series. I get 1.5 volts. We get 1.75 volts out of that, so I have plenty of voltage. So now I can take that, put a protective coating on it, put my cobalt catalyst there. For my hydrogen catalyst, it only took us a month to make this. We did a nickel molybdenum zinc alloy on the other side. So when the holes are made, so what will happen, I could walk over there, but I just don't have the energy. You just put this thing in a glass of water, put it right up to the windowsill, and what you see is sunlight comes into this. Here, I'll walk over here. When I first did it, all I did is just watch it. But now I don't care anymore. But when I did it, because I spent my whole life trying to do this, and when it happened, I just sat there watching it all day. So what's happening now is a hole goes up when the sun comes in. That comes to the front, one hole. The electron goes to the back. That's how my voltage ramp is. Then I got to do it a second time, a third time, and a fourth time. When it's 4 times, oxygen comes off. The protons are here. They run around the back, and you make the hydrogen. And it bubbles all day with the sun. It's running at a current that can keep up with the sun. The silicon cell I made, we can now get this up to a solar to hydrogen efficiency of 12.8%. So that's sunlight into hydrogen, a real efficiency. That looks like a hamburger. So think about it. The silicon is the hamburger. The cheese is the protective ITO. The top bun is the cobalt catalyst, and the nickel's the bottom catalyst. So it looks like a hamburger. But more importantly, it's how you build a McDonald's hamburger. There's no wiring. I don't need EE people to wire everything, okay? No membrane. It works in any water. Simple engineering. Just layers. I can make this whole thing using chemical vapor deposition. So I can make the amorphous silicon with CVD. I can do the doping with CVD. I can make the FTO with CVD. We've developed the chemicals to do the gas absorption and then CVD. So I can literally just CVD this as the system's running by, just like you would make a hamburger. All right? So that gets us to 12.8% efficiency. What will you do with hydrogen? So this is the problem. So now we have a nice discovery, use any water source, and now I have to convince the entire world to use fuel cells. I have enough problems, right? And we don't have an infrastructure for fuel cells. So the only thing you use hydrogen for is to do this. You blow up balloons with it. I mean, that's what we do with hydrogen, right? You have fuel cell cars, but you got to have a hydrogen infrastructure for it. You could have fuel cells at your house. You could split water at your house and then feed it to a fuel cell and you could power your house. But now I have to convince the housing industry to put in fuel cells everywhere. By the way, you should. But remember, I told you, you have an $8 trillion investment paid off. So it's very hard for me to convince you to change that $8 trillion paid off investment. So you can complain about it, which I did for 2 years. And said, investors are awful, I can't stand all of you, because they all want a return on investment in 4 years. The other thing you could do is say, all right, I really haven't gone the full distance in photosynthesis, because now I got to take my 4 protons and 4 electrons, 2 moles of hydrogen, combine it with CO2 and make stuff, carbohydrates. And like I told you, what do you do here? Or make liquid fuel. When you burn the liquid fuel, you're really just getting the hydrogen back out and you're dumping the CO2. So you really are burning hydrogen, but you're just decomposing a hydrocarbon to get the hydrogen back out. And that's what you're really doing. Here is water splitting, and that's the voltage, 1.23 volts. And remember, G equals minus NF delta E. So now I'm going to show you half reactions for fuels. Carbon dioxide to methanol, 0.17 volts, downhill. So once you have the hydrogen to make methanol, it's kinetically challenging, but it's not a thermodynamic problem. It's a dark reaction. Methane, downhill. Isopropanol, isobutanol, isopentanol. I'll show you why I chose those. All downhill. So that's my point. Once you have the hydrogen, combining it with CO2 is not a thermodynamic issue. It's a hydrogen storage issue. Where does photosynthesis fail as an energy storage medium? Not as an energy machine. It's beautifully, beautifully efficient. But it doesn't store it, right? Nobody told a plant 2.6 billion years ago, we're going to have an energy problem. Please evolve to an oil well and store it. What does a plant do? They're no different than you. What are you going to do today? You did today. You ate energy, calories. You try to burn the amount of calories you ate. If you don't, you keep storing it, right? So plants are very efficient with energy, but they're like you. They eat calories from the sun. I know how much, P680, P700, I know they're two absorptions. And I know the thermodynamics for oxygen evolution and NADPH. So I take that energy, subtract it from that energy. It's using the excess energy to power all these other processes metabolically, just like you're powering, you ate your food to power its metabolic process. But in terms of stored energy, oxygen and hydrogen, when I do the simple algebra, you're at 28%. Sunlight into oxygen and hydrogen. Then this plant doesn't absorb the whole solar spectrum, like my artificial leaf. And so when I take the solar spectrum and integrate it to the absorption profile of the chlorophylls and light harvesting complexes, 28% goes to 10.5. A photosynthetic organism can never store theoretically more than 10.5%. Most plants store 1%. Right? So they store 1%. Switchgrass, soy. So that is the limit of photosynthesis because, like I said, it's doing all these other things with the energy, not storing it. But I just care about storing energy. So I can take this piece where I'm losing a lot of energy for storage. I'm not having to run metabolic processes. And what I'll do is take that and get rid of it because the whole photosynthetic membrane is just PS1 and 2 is only meant to split water, oxygen and hydrogen. So I'll get rid of it, but I need to feed hydrogen into a metabolic cycle. I got to still get to a Calvin cycle. So how will I do that? We had the idea we'll take a bacteria, Ralstonia eutropha, and if I can genetically, because of genomics now, I can insert genes anywhere I want. This is called synthetic biology. And I'll insert a gene into Ralstonia and put an excess of hydrogenases in the membrane. And if I do that, what does a hydrogenase do? It takes hydrogen and converts it to 2 protons and 2 electrons. And if I couple that on the back end to an NADPH reductase, that then goes, I'm leaving out all the cycles, biology. NADP reductase makes ATP, and once I have ATP, the bacterium's good to go. So this is a way for me to take the energy stored from the artificial leaf in the form of hydrogen and convert it to ATP by genomically encoding Ralstonia with a hydrogenase. And then I can run a Calvin cycle. And that's what we did. So in this, we took the Ralstonia. This is a mutant form because I've genetically mutated it. And this thing can take hydrogen, through the hydrogenase, it makes NADPH to ATP. I can run a Calvin cycle. I can get to acetyl-CoA. And from acetyl coenzyme A, I can make biomass. But I can even be sneakier. So biomass is great. We make lots of lipids. Then you can go get a chem engineering friend, and they have to turn the biomass into a fuel. That's what chem engineers do. But say you don't even want to hang out with chem engineers. I could put 4 other genes in, because once I'm at acetyl-CoA, how about if I put a ketodiolase gene in, an acetoacetyl transferase, acetoacetate decarboxylase, and alcohol dehydrogenase? Why will I do that? You open your organic chemistry textbook. What does a ketodiolase do? It breaks the acetyl-CoA bond, carbon bond, and it joins it with another carbon bond. That's what a ketodiolase does. The CTF gene, it cuts this off, basically does a hydrolysis reaction. I then decarboxylate, that's what this ADC gene does. Now I'm to acetone. And then I hydrogenate it. Now I'm at isopropanol. So I've avoided making biomass, and what I do at acetyl-CoA is I do all the chemical engineering genetically inside the bug. So we did that. And we got, with a 12.8% driver, we got 1.6% biomass. So if I don't put these 4 genes in and just run it all to lipid inside the bacterium, sunlight in, I just weigh it. This is like a real efficiency again. My bacteria are growing. It's almost all lipid. So I just weigh my bacteria. Sunlight in, how much bacteria did I make? And it's storing it at 1.6%. And I told you the best growing crops are here. So we've now got to the best growing crops. I can go the other bug, this other genetic mutation, up to there's just biomass. This is the 4 other genes. And then I can do 0.6 to isopropanol. And we did that a year ago. And that kind of made us happy. But we were also confused because these bugs, I'm going to show this graph first, only lived if we put 2.7 volts on them to drive water splitting. Now, I told you thermodynamically water splitting is 1.23. So at 1.23 volts, I'm making the food for the bacteria. And I want to emphasize this. The only things we give this bacteria is hydrogen. That's it. That's how it lives. We charge up the solution with nitrate and phosphate because it has to do DNA synthesis. But then it just eats hydrogen. We give it no other nutrients. Its total food is hydrogen because of that trick we played. But to generate the hydrogen, we have to put a voltage in. And we needed to put 2.7 volts in. If we put less voltage in, look at, they all died. And that's weird. You don't usually electrocute something to keep it alive. But we had to electrocute. We had to keep putting more and more current into it to make it live. So, and that's bad from an efficiency point of view because the driver, the energy driver, thermodynamically is 1.23 volts. But to make the system work, I'm having to apply a voltage of 2.7. So that means my sealing efficiency is under 50% to keep these bugs alive. So what was going on? And because there's a big bioelectrochemistry literature, we spent 6 months of our life thinking we're making oxygen. Oxygen can make reactive oxygen species, things like superoxide or H2O2, and kill the bug by interrupting its DNA. That's what ROSs do. So we were, because there was this literature on just in general bioelectrochemistry, all the biologists were concentrating on the oxygen side. After 6 months, we realized they're perfectly happy on the side we're making oxygen. It was on the side we were making in their food that they were dying. And then, this is good old inorganic chemistry, Latimer diagram. At pH 7, where the bugs live, you make hydrogen at a potential of minus 0.41. At 0.33 volts, just inside that, you can reduce oxygen to superoxide. Once I get superoxide, I can make ROSs. So my current, which was supposed to be making hydrogen, a little bit, we were still making hydrogen. We could see all the hydrogen. But enough of the current was getting diverted to making ROSs that was killing the bugs. And only if we got to 2.7 volts and kinetically overdrove water splitting could we avoid the ROS. We figured that out. So what do? The first thing is you just keep killing the bacteria. You challenge them with superoxide, and they died, and they died, and they died for 2 weeks. And then a few lived, and a few more lived, and a few more lived. Because like any good organism, it doesn't want to die. And it did a genetic mutation. And we genomically sequenced it and found it put in, this is the key one, the ones that were getting challenged with superoxide put in a 45 base pair deletion to get rid of a membrane efflux gene. It got rid of it. And the superoxide was going through this membrane efflux gene. So that's one way, but I'm an inorganic chemist, so there's another way. My nickel molybdenum zinc catalyst was making superoxide. And so we found if we took cobalt metal, pure cobalt metal, and infused 5% phosphorus into it and made a cobalt phosphide alloy, like here's platinum. When you try to make hydrogen with platinum, that's what people use all the time. Look at what happens. You make a ton of H2O to it at pH 7. But this thing makes no superoxide. So now we have a catalyst system that's totally biocompatible. We can drop our current now to 1.7 volts. So that means I have a much higher efficiency. So what we do, and here's the real data, we take a few bugs. You don't even make a lot. You just take a few genetically mutated bugs. You throw them in solution. And then you seed it. Then you turn on hydrogen. And what will happen is the bugs go into exponential growth phase, right? 2 go to 4, 4, and then you get an exponential growth phase. So we let them grow to whatever optical density we want. We go to an optical density of 99%, optical density of 2. That's just light scattering. That's how the biologists measure density in an easy way. Then what we do is we adjust our hydrogen flow to be at the Km of the hydrogenase so that we go into steady state. Over the course of weeks, some die, but we can adjust the hydrogen relative to the bifurcated alcohol pathway so that we only use some of the hydrogen to make new ones, and we go into steady state. So we just maintain the whole thing at 2. And then all the extra hydrogen can be used for whatever we want for isopropanol. So for isopropanol, we can make 7.2%. If we just if we don't put in the genes to make a fuel, we can take sunlight to biomass at 10.2%. Right? So if you want a bunch of lipid. Or we can do this other genetically mutated strain and make isopropanol at 7.2%. Why at 7.2%? We think it's higher, but what happens when you get a cut? You put rubbing alcohol on it to kill the bacteria. That's isopropanol. So what we did, and isopropanol soluble in water. So what we did is we put different genes in, and we could make isobutanol and isopentanol. Nice thing about those alcohols, they phase segregate from water. I don't even have to do anything. You can also put other genes in there. Polyhydroxybutyrate. I can make them make plastics. So I have a way to renewably make plastic. I could put genes in to make steroids in medicine. See, this is synthetic biology now. It's not. We have the trick of interfacing to the sun via water splitting. You can make long-chain hydrocarbons. We have C10, C12, C14. That depends. In a fatty acid synthesis, it depends on what thioesterase we put in to just snip it and bring it out of the fatty acid cycle. We can make odd-chain hydrocarbons if we put propionyl-CoA, 3 carbons, and then we add 2 at a time, and I can make odd-chain hydrocarbons. Okay? So we've done that. That we haven't published yet. A 1 liter reactor at an OD of 2, these guys fix 500 liters of CO2 per day to make a fuel. All right? That doesn't solve your CO2 problem, right? What happens when you burn a fuel? You get the CO2 back. So this is a carbon neutral fuel cycle using the sun to make fuel. Your 400 part per million to 550, that's your problem. I don't care. I can't help you with that. But I can help you from not digging any more of it out of the ground. And these things, remember, they have natural CO2. I don't have to do CO2 concentration. They have carbonic anhydrases, just like grass, just like trees. So they're doing the CO2 concentration internally. The biology is doing a lot. The other thing I forgot to mention, these alcohols, this one, the isobutanol, isobutanol, 30 proton, 30 electron, proton coupled electron transfer rate. So it's managing a lot of chemistry. in doing this. The other nice thing is, I told you it's doing CO2 concentration. I don't have to do any technology up front. I just need a bug fermenter. That's it. They're sucking the CO2 in. This has to be engineered properly. I'm not minimizing that. But I don't need to do any special CO2 concentration up front. My bacteria don't need to see sunlight. Algae needs to see, a photosynthetic organism needs to see sunlight. So that's a complicated reactor design because you have to make sure you mix and push water and each algae sees photons. But remember, my artificial leaf is doing water splitting. That's looking at the sun. These guys are eating hydrogen. So I don't have this complicated reactor design. Because I'm 10 times the efficiency of regular organisms, my artificial leaf only needs 10 times as less space, and it can be in the desert. I don't need to compete with crop or land fuel sources. So this has a lot of advantages, this segregation of inorganic chemistry from biology. Use what biology is good at, and use what inorganic chemistry is good at. Inorganic chemistry is good at the solar part, biology is good at the dark part. That's what we did. And that all happened because of the self-healing catalyst. That allowed me to be in water. That allowed me to do artificial leaf integration. That allowed me to integrate to biology. Finally, I kind of alluded to this. The trick is we put a nose on the bacterium by genomically encoding a hydrogenase. So inside, I can genomically put anything, including all this. I showed you one for plastic. Stay tuned. We took a different organism. We introduced a nitrogenase, and they do the same thing. They suck. I have friends who try to do nitrogen reduction to ammonia at 7 turnovers. They publish a science paper, and they go, woohoo! 7 turnovers is not going to cure the food world supply. These bugs literally suck nitrogen in, different bug, different genomic engineering, and they make fertilizer. And matter of fact, it's a little dangerous, so don't do this at home. But we can take the bugs, I'm doing this at Harvard in the greenhouses. We just throw the bugs in the dirt. We float a little hydrogen over it because that's all they need to do is to eat. And in the Harvard greenhouse, our crops are growing 6 times faster than crops just normally growing because the bugs are actually doing nitrogen fixation and fertilizing them in the ground as they're sitting in there with the plants. So you'll be seeing all this. So this is kind of cool because I now have a way to, I can now do solar energy in your backyard with my little hamburger. Now if you're poor, if you have these bugs in the artificial leaf, you don't need a Haber-Bosch plant to do nitrogen fixation. And we're showing where the rubber hits the road. The plants grow faster by a factor of 6, right? So that makes us all happy. We're translating this into India. I've gotten Harvard to pass all the IP through to the Institute of Chemical Technology in Mumbai. And I'm going to have Indian scientists in India do the scale up, let them start the companies and become rich off it. Because I want it to work in their society, not here with investors who want a 4-year return on investment. I'm done with these nitwits. Okay. Finally, I just heard this morning. Kane, a potential vice president for you guys, his wife was on the news this morning saying, I'm so tired that we're talking about, you know what we've been talking about in America. She goes, we need to get to real issues like saving the planet. And I want to give you a message of hope. You're going to keep hearing how much trouble you are with the climate, and you are. God bless you all. Okay? And then I always hear people say, we got to save the planet. We got to save the planet. And there's lots of anxiety about that. Just before he died, I got to know this guy because I do a lot of public stuff. And he heard me say, I used to say, save the planet. And then he taught me something. So I want to teach this. And this will make you feel better. When you feel lots of angst about where we're headed and will we die, suffocate with CO2, the planet. He said, the planet's a living organism. And like what happens when you have an organism? When you have an invader, bacteria, like Ralph, it's going to kill you or bother you, you have an immunological response of the organism to eliminate the irksome intruder when sufficiently compromised. And Vonnegut, being a little outside the box, just said, look, the planet is just one big organism, and she's beautiful and wonderful, and she has an immunological response system. So Dan, don't worry about it. As we carelessly choose a path to suffocate the planet in CO2, don't worry, the planet's immunological system will respond and just eliminate human beings, and the planet's going to be just great. And that always makes me feel happy. Like, if none of this works, it's going to be okay. Well, I'll be dead, but the planet's just going to be chugging along. And so just think about that when you get really depressed, because that makes me feel happy too. So with that, I'd like to thank you for your attention. I'll answer any questions you have.
You just want to take questions?
Yeah, I'll take them. Yeah?
Do you see much mutation in the bugs that you
Yeah, so one thing is if you get to like microalgae, there are people trying to build microalgae plants at 3%. In Denmark, they've gotten to 7%, but they're so highly engineered, there's a genetic back pressure. So we chose Ralstonia, those 4 mutations. So first the hydrogenase 1 mutation. But the back pressure is practically Zippo on these. So that's what makes Ralstonia good. Ralstonia isn't a tremendous organism. One thing I haven't talked about is throughput. I kind of did. 1 liter reactors, 500 liters. But you could go faster and faster and faster with faster hydrogenases, which the Ralstonia won't tolerate. So there are other organisms, and my ex-student, Michelle Chang at Berkeley, has used an organism taking off on this approach to do methane. It has very fast hydrogenases, but it has this junky synthetic biology, unfortunately, the organism. But she did some beautiful science, but there's a back pressure. So we chose this because it's kind of like a rugged synthetic bioorganism. But you're right, if I get too far afield, when they die, they say, forget this, I'm just going to genetically mutate back to who I used to be. Yeah. But these are good bugs. I like them. Yeah.
So, just when you solved the hydrogen problem, you generated hydrogen, then you said, putting hydrogen together with CO2 is kind of hard with the inorganics.
Yeah.
Go biology.
Yeah.
But what's the problem there?
Okay, so the question is, why am I even messing around with bugs? Okay, why not make a catalyst? Which, by the way, is what most of my friends are doing, and I love that science, and it's really interesting. We just wanted to know, could I make liquid fuel? So the first problem is, this other talk I give, which is very inorganic-y and mechanistic, it took me over 30 years to split water. So proton-coupled electron transfer is a hard thing to do. And if you're not good at it, you get big kinetic barriers. And water splitting is 4 electrons and 4 protons. Some of these things, 50 protons and 50 electrons. So that is bothersome. The second thing is, for a regular catalyst, you could try to reduce CO2, but under reducing conditions, there are protons around. So it's much easier to just make hydrogen. And so what you have to do with inorganic catalysts is try to suppress hydrogen production, which is practically impossible to do. These bugs do it naturally because they're pulling the carbonic anhydrase in and the hydrogen is getting converted to ATP. So you don't have that problem. And then thirdly, just like we do now, we do CO2 to fuels. It's called Fischer-Tropsch. Again, large chemical plants. Everything I told you we can do with large chemical plants. The idea is to do it in a low capex way in the backyard, distributed for the poor. This is why we do research. I'm not trying to replace Fischer-Tropsch, but Fischer-Tropsch is a mess because you have to do so much separation because it's not selective. So when you get to PCET, non-selectivity, and the hydrogen problem, so for regular catalysts, you have to concentrate CO2 to try to outcompete even hydrogen. And the best work is my ex-student, Matt Cannon, at Stanford, and he's gotten to ethanol at 60% conversion efficiency. Before that, the best metal catalysts were like 2% for a carbon product. So that's why we went to biology, because it does all this other stuff so well. Yeah?
I wanted to ask you the big picture question since you show all these McDonald's analogies.
Yeah.
So for your total throughput now, what's your cost?
Yeah.
For developing
$10 per pound.
You got $10 per
No.
pound.
I have hydrogen at $4.45 per gas gallon equivalent. So what's that? A kilogram of hydrogen is equal to a gallon of gasoline in energy density. And we can do $4.45 a kilogram of hydrogen, which is your basic weight question. But now I have a whole question with the bugs, but it's a simple reactor design. But I still can't answer that. So I'm serious. What I'm going to do, I'll just put the whole thing up. Right now, as I'm speaking to you, I'm monitoring 1,000 power plants in India with carbon emission. In the state of, there's 3 states. The state where Mumbai is housed is the Institute of Chemical Technology, which is the premier chem engineering school in India. So what I'm going to do, and I'm doing this with Michael Greenstone. He's a famous environmental economist at University of Chicago, and Rahini Pandey. They're doing the left side, and that's generating revenue, which is going for revenue generation in these states. But some of that revenue is going to go into ICT, and I am now past everything I just told you, all the IP to ICT for them to develop. And I've generated a revenue stream. And they're going to answer your question for me. And so it's so great. Not only am I doing it in India, it's not my problem anymore, it's their problem, which makes me happy. The other thing I will tell you is NREL, EERE, is working, they're modeling this right now because they're really excited because they had for years been modeling photosynthetic organisms and algae, and they're realizing how much costs they're offloading with this. So at least on paper, in 6 months, EERE will have a full, they're doing a full systems analysis and will have the price for me. But it's looking good because of what I said. These bacteria can sit in the dark. And so I just have, but getting hydrogen in and CO2, you got to do this flow issue. There's real engineering here to do. And I don't want to minimize it. And cost, again, you want to do it cheaply. Yeah?
Your choice will work in the system, like if you're looking at the Cuban structure, the oxygen evolving complex has the calcium manganese. Why not go with the manganese?
Manganese? So we have, and by that, yeah, we've done manganese. And by the way, manganese is spectacular in that it has a 4th order curve. So when the curves cross, they cross at minus 0.5 pH. So I don't know if you know it. Think about what I'm saying. I can take a manganese oxide, put it in concentrated nitric acid, and it doesn't decompose, and I can do water splitting. So that sounds great. What doesn't it do? If you look at the pore bay diagram of manganese, when we get to too high of a current density, you go to permanganate, because there's permanganate, a molecular species, shows up in the pore bay diagram. And so then I can maintain the stability in my self-healing, but then I get to current densities where I make a new molecular species that it decomposes. So as long as I stay below 1 milliamp per centimeter squared, manganese works like a charm. But over an amp, if I run high current, permanganate shows up. And you run higher current because you turn up the voltage to drive the system harder. But just before I came here, I think we've solved that problem. We're using structural oxides where we only dope a few manganeses in. And the structural oxide, we use pore bay diagrams. They're stable, and we're able now to get manganese way over 1 milliamp without going to permanganate. This also works for nickel. So it's manganese, nickel, and cobalt. And we have all these self-healing cycles working for those metals.
Calcium plays that role. The calcium is there for the actually replace the calcium with strontium.
Yeah, and strontium. So calcium is still a role people wonder about and could it be deprotonating? In our system, we know the mechanism, and the alkali metal isn't that important for it. But I think in the structure of OEC, OEC is super special. One thing I didn't tell you, our catalyst is 3 times slower than OEC. We're overall 6 orders of magnitude faster. Why? The photosynthetic membrane takes up a surface area of the whole room, and there's a pinhead called the manganese, and all that current is going through one catalyst. In my artificial leaf, I fill the room with catalyst, so I can go 6 orders of, so I can be slower. And so the manganese cluster is very fragile. The manganese-oxygen bonds are getting activated or hardly holding it together, and it's the D1 protein, and I think the calcium ion that's setting the structure. In my catalyst, the internal metal-oxygen framework is setting it. So I'm imposing a kinetic barrier. But I don't have to be as fast because I'm doing technology. I can fill the room with catalyst. But the manganese, if you ask me what we're doing in our group at a fundamental study, we're trying to make oxide architectures where we can put unstable oxides, meaning high spin, weak metal oxygen bonds, to see can we make catalysts at super high turnover frequency with this idea of imposing structure with, say, a nanostructure. But it's remarkable, OEC. But we can do it with manganese, but even in our compounds, we're still holding it together with internal metal-oxygen bonds. Anything else?
This is a silly question, but you keep mentioning...
No question silly.
You keep mentioning McDonald's hamburger. You all don't have Burger King in Boston?
I went to McDonald's because I met a CTO. I literally did. I couldn't believe it, and I was so impressed. I'm sure Burger King has one too.
All right. Let's thank our speaker again.
Thanks.